Hi there, and welcome to our lecture on ionic and covalent bonding. This is going to be reaction 2 of Unit 4. Our objectives: why do atoms form bonds? How do ionic bonds form? What do atoms joined by covalent bonds share? What gives metals their distinctive properties? And how are polyatomic ions similar to other ions? So starting with our first question, why do atoms form bonds? So generally atoms join to form bonds so that each atom has a stable electron configuration. We're not necessarily going to worry about the term electron configuration so much, but basically they bond so that the electrons are happy, and we call that being stable. And we've got two basic kinds of chemical bonding. We've got ionic and covalent. So comparing or contrasting those two types of bonds, looking at ionic compounds, the structure of those very networked, very fixed, whereas covalent compounds we view as being molecules, so different items bonded together. As far as the valence electrons go, ionic compounds, the electrons are transferred from one atom to another atom, and when they're transferred, they're then referred to as ions. With covalent compounds, the electrons are shared, so those outermost electrons are shared between the atoms. As far as electric conductivity, with ionic compounds, it's good, and when melted or dissolved, so we'd have to put salt in water, dissolve it, and we do get some electric conductivity that way. With covalent compounds, if we put sugar in water, we don't get any kind of that is produced. So it's poor as far as electric conductivity is concerned. At room temperature, ionic compounds tend to be solid, and covalent compounds can be solid, liquid, or gas. Melting and boiling points, the ionic compounds melting and boiling points are generally high, whereas with covalent compounds they're generally low. Alright, so how do ionic bonds form? Ionic bonds form from the attraction between oppositely charged ions. An ionic bond, just for definition purposes, the attractive force between oppositely charged ions, which form when electrons are transferred from one atom to another. Ionic bonds are formed by the transfer of electrons. So two atoms tend to form an ionic bond when one atom has more attraction for electrons than the other. Ionic compounds are in the form of networks, not molecules, so they take on this very structured, very fixed appearance. That's why we tend to find them as solids at room temperature. A formula unit is the smallest ratio of ions in an ionic compound. And when melted or dissolved in water, ionic compounds conduct electricity. So let's look at sodium and chlorine. So we're going to make its table salt here. If we took a look at the sodium atom, we can see that we've got this inner ring that has a stable 2 electrons. The next one out has 8. And then our outermost shell, our valence electron, we only have 1. What we want in this outer shell is we want to have 8. So sodium would like to have a full shell, so it wants to have 8. It has 1 right now, and let's say it's in close proximity or around some chlorine atoms, and you'll see that chlorine's got 2 inner electrons, 8 on the next outer, and then 7 valence electrons, 7 outer electrons. So it wants to have 8 here as well. So when the sodium atoms and chlorine atoms are close together, what's going to happen is you can ask yourself this question. It's going to be easier for a sodium atom to lose 1 electron or gain 7. And it all comes down to energy. Which one is going to take the least amount of energy? Because atoms are lazy. They want to use the least amount of energy in order to become stable. So with sodium here, it's going to be easier for this one electron to leave the sodium atom. Now becomes a sodium ion, and it becomes a positively charged, so it now gets a positive 1 charge. And that is because electrons are negatively charged. So in a neutral sodium atom, we've got 11 protons and 11 electrons. But if one of these electrons leaves, we still have 11 protons, 11 positively charged protons. But now we have 10, so 8 here and 2 here, 10 negatively charged electrons. So we've got one more positive charge in the nucleus than we have electronic charges on the outside neutralizing. We get an overall positive charge. So where does this electron go? Well, we've got chlorine over here that's got 7 electrons in its outer shell. It's going to be easier to gain 1 electron than it is going to be to lose these 7 electrons. So this 1 electron comes over, and we now have a stable chlorine ion. So we call this an ion now. Change its name from atom to ion. Got a different number of protons to electrons. Chlorine has 17 protons in the nucleus, has 17 electrons. Well, now it's got 18 electrons because it gained 1. So the difference between positive 17, or if we take positive 17 minus, we now have 18 negative electrons. So what's going to happen is we get a chlorine ion that has a negative 1 charge. And when this happens, we've got another visual here of what it changed to, what these atoms are now ions, what these ions are now. And because of this positive charge with sodium and this negative charge with chlorine or chloride ions, there's an attraction. So this positively charged sodium is now attracted to this negatively charged chlorine. And here we've got a formula unit, so we've got one formula unit formed by, in this case, calcium fluoride. So we've got 1 calcium ion bonding to 2 fluoride ions, so we've got 1 formula unit. And you can see here that calcium fluoride, being an ionic compound or ionic bond, forms this kind of structure. We call this a crystalline structure that it forms. So we sometimes refer to ionic compounds as forming salts, because salts take on this very structured appearance. Alright, covalent bonds. What do atoms joined by covalent bonds share? Atoms joined by covalent bonds share electrons, and they're sharing those outermost electrons. Those valence electrons are being shared now. So a covalent bond is a bond formed when atoms share 1 or more pairs of electrons. So now we can share more than just 1 electron. We can share several electrons. Compounds that are networks of bonded atoms, such as silicon dioxide, are also covalently bonded. Covalent bonds usually form between nonmetal atoms. Covalent compounds can be solids, liquids, or gases. In a chlorine molecule, Cl2, the atoms share 2 electrons. We'll just do a little visual real quick. So just looking at the innermost electrons for chlorine. And I know we didn't talk about Lewis dot structures, but if we just show the 2 electrons that a chlorine is sharing, there still is 6 more pairs of electrons on the outside of each of these chlorine atoms, or ions. Put those in visually. So you can kind of see these are representing the valence electrons. So each chlorine atom has 7 valence electrons, so what happens is we get this pair that's in the middle here that's attracted to each other. So one of these is from one chlorine atom, the other one would be from the other chlorine atom, and when they're in a solution or mixed together, they will share those. So this is one covalent bond. So here's another way to represent this. Chlorine atom with 7 valence electron is bonded to another chlorine atom with 7 valence electrons. When they come together, we've got this covalent bond. So now each chlorine thinks it's got 8 valence electrons, even though at any given time the electrons may be more on this atom, or they might be more in here, or maybe they're in the middle. So we don't know for sure. All right, atoms may share more than one pair of electrons. 2 pairs of shared electrons, or 4 electrons, form a double covalent bond. 3 pairs of shared electrons, or 6 electrons, form a triple covalent bond. And then double bonds are stronger than single bonds. Triple bonds are stronger than double bonds. And we can represent these double bonds, like for example, oxygen bonded to itself. So an O2 molecule would be represented as this. So these 2 lines represent 4 electrons or a double bond. And then nitrogen will bond to itself. So a nitrogen molecule, an N2 molecule. We've got 3 bonds, and each one of these lines represents 2 electrons. So we have 6 electrons that are being shared with this triple, or this covalent, triple covalent bond. So 6 electrons. And we've got 2 more electrons that will find themselves unbonded. We call these unbonded electrons outside the nitrogen. And if you'd like, we'll do it for oxygen up here too. And what happens is we typically find these electrons are going to want to try to get as far away from these double bonds as possible, but then not interfere with the other electrons. So they'll kind of be off at an angle like this when this bond occurs. And we get this same representation here. What I would probably do is they represent these electrons here on oxygen at the top and the side because of their software program, but these would actually shift around a little bit because you have a lot less interference between these alone pair electrons, unbonded electrons, and this double pair electron, and there's some space here that these electrons can shift around and create a little more or a little less interference. Here's just another visual of how we can show those electrons being shared. Alright, so more on covalent bonds. Atoms do not always share electrons equally. We call these non-polar covalent, non-polar covalent bonds will share electrons equally. When 2 or more atoms of different elements share electrons, the electrons are not shared equally. This is polar covalent bond. This is when we have 2 atoms that are bonded together that are different. They're still covalently bonded, but because one has more of an attraction for the electrons than the other, we'll find the electrons more on that element or atom. And we call that electronegativity, just the attraction or tendency to attract electrons. So we've got 2 examples here. Notice we've got 2 atoms that are the same that are bonded together. Maybe call this a chlorine atom. Bonded to a chlorine atom, it's sharing a pair of electrons. But because these atoms are the same, essentially, the electrons are going to be distributed fairly evenly between those 2 atoms. Same thing with a hydrogen molecule here. However, if we had, say, chlorine bonded to a hydrogen atom, these electrons that are being shared are going to be attracted more towards the larger of the molecules. So this big bad chlorine wants those. So chlorine wants those electrons more than hydrogen does, or is able to pull. So consider or think of chlorine as kind of the bully here. It's going to bully hydrogen around because it's bigger and can do that. And this is just the visual going the other way. So these electrons are attracted to the larger of the molecules because there's more of an attraction. There's more positive molecules within that atom to attract those electrons to it. So comparing ionic and covalent molecular compounds, typically ionic compounds form this very fixed structural shape between sodium and chlorine, which also allows it to have a higher melting and boiling point, whereas say sugar doesn't necessarily have as fixed or structural attraction, so it'll boil and melt a lot at a cooler temperature. All right, metallic bonds, what gives metal their distinctive properties. Metals are flexible and conduct electric current well because their atoms and electrons can move freely throughout a metal's packed structure. A metallic bond defined as a bond formed by the attraction between positively charged metal ions and electrons around them. So if we have our comb, we're doing our hair in the morning, we've got our comb, our brush, we're brushing our hair. The movement of the comb through our hair is going to cause a charged or a static charge on the comb. We're going to get these uneven distribution of electronic molecules, so that's why we get this electronic charge. We have a buildup of either more negative or more positively charged ions on the surface of this comb. I think this is the last thing we have. Polyatomic ions are similar to other ions, and we're not going to worry about these too in depth, but a polyatomic ion acts as a single unit in a compound, just as ions that consist of a single atom do. So a polyatomic ion is an ion made of two or more atoms. There are many common polyatomic ions. Here's a few examples here. Hydroxide. Notice that this is a molecule, so we've got oxygen attracted to hydrogen, but because there's only one hydrogen, we still have an overall negative charge with hydroxide. A carbonate, we've got oxygen bonded to 3 carbons. There's still overall -2 charge on this carbonate ion. Ammonium has 1 nitrogen, 4 hydrogens, so it has an extra hydrogen bonded to it. Because of that, it has an overall positive charge. And what happens is hydroxide, carbonate, ammonium, there's several others, sulfate, nitrates, and so on. These will act as a single unit within a compound. So it'll act as a part all by itself. So we put these parentheses here to group the atoms. So, for example, the formula for ammonium sulfate is written as NH4 2SO4, not N2H8SO4. So we're grouping 2 polyatomics here. We've got ammonium and sulfate that are kind of grouped together. To separate those out, we get 2 ammonium because ammonium has a +1 charge, sulfate has a -2 charge. So in order to cancel that -2 charge out, we'd have to have 2 positively charged ammoniums. Some names of polyatomic anions relate to their oxygen content. Just real quick, ATE ending is used to name an ion with more oxygen atoms. So SO4 is sulfate, NO3 is nitrate, ClO3 is chlorate. And then ITE ending is used to name an ion with fewer oxygen atoms. So looking at those same substances, but taking away one of the oxygens, SO3 is now sulfite, NO2 is nitrite, ClO2 is chlorite. So just by changing the number of oxygens, and we can go up or down from this as well. So they could lose an additional oxygen, and then their name changes again, or we could have gained an extra oxygen from the sulfate ending, and we get yet another name. We're not going to worry about that for this course. And here's just a table of some common polyatomic ions. So, thanks for listening.